All right, lastly, for V RMS, well, V RMS actually equals the square root of V average squared. So in order to do that, you have to still take the original function and you multiply it by V squared. The reason you do that is just by definition of RMS, root mean squared, you have to first square the velocity, then you add it up by integrating, then you have to take the square root of the result of that. And so you pretty much are taking V average squared is where you're going to start with. So your integration from 0 to infinity, the V squared, when you put it in, you end up with V to the fourth E, alpha V to the fourth E to the negative alpha V squared dV. And so we know when we run into a problem with how we integrate this in our Cartesian format, it actually won't work out. There's nothing we can do, so we actually have to kind of play around with it. So where our little trick comes into play, we can just take a basic integral, 0 to infinity, of an e to the negative alpha x squared dx. When we double this, not double, I'm sorry, we're going to square this, square both sides. We'll do one variable in x and one in y. And when you just put these together, we're going to just add the exponents. The I is just what the answer to the integral will be, just some integral.
Just some red nature.
Yeah, you call it anything you want. It's just to show that now we're squared. We squared everything, so that's what makes this so true. Sweet. Okay, and so then we can take this now into polar coordinates. And so in a polar coordinate, x squared plus y squared is r squared, and you get that just from the unit circle. And then when you change your variable, your dx dy equals r dr d theta, r being your Jacobian. And so the integration now is going to become r e to the negative alpha r squared dr d theta. Now for your limits, this is what you have to watch for. So we went from 0 to infinity on the x and 0 to infinity on the y. So if you just look at a graph, we're just talking about quadrant 1. So in polar, we're going from 0 to pi over 2. And then your radius would extend out to infinity to sweep all that. So you gotta make sure you watch the change of the limits. So over here we get 0 to pi over 2 d theta. And right here I'm gonna do now we can do a u sub to get rid of this r squared in the exponent. U equals r squared, so du equals 2r dr, same as du over 2 equals r dr. So we'll plug all that back in. And again, if you plug in 0 for r, you would get infinity. Or you would get 0. And then if you plug in infinity for r, you would still get infinity for u, so the limit actually stays the same. And you're going to get e to the negative alpha u du. And so this is a pretty easy integration, right? You just get pi over 2. Well, can't forget my 1/2 that I pull out front. Multiply that by my 1/2. Then the integration of this is just, we got just -1 over alpha times e, negative alpha u, 0 to infinity. So after we plug in all of our limits,
We run into a similar thing here. When you plug in infinity for u, this goes to 0, 0 is allowed. When you plug in 0 for u, this goes to 1, and so what you're left with is the negative 1 over alpha. I'm sorry, you're minusing the negative, so it's actually a positive 1. And so you just get pi over 4 alpha. Now remember, this equals I squared. So that means the integral would actually equal 1/2 square root of pi over alpha. And so that's going to come back to here, what this equals. Come over here, actually. And then, so now if you take original integral, you take the derivative with respect to alpha. E with alpha x dx. It's the same as moving the derivative on the inside, which would give you, and again we're doing a derivative with respect to alpha, so we get a negative x squared e to the negative alpha x squared dx. It should just be the derivative with respect to alpha of our answer right here. Which is going to be negative 1/4 square root of pi times alpha to the negative 3/2. And then we're going to just do this whole process one more time. With respect to alpha of this integral. Move the derivative inside. You get x to the 4th. E to the negative alpha x squared dx, which is the derivative with respect to alpha of this answer. Which is 3/8 square root pi times alpha to the negative 5/2. The negative 5/2. And since this setup right here is exactly the same as this setup right here, we just have a constant there, but everything is exactly the same. You can actually just substitute your same alpha in here. Make sure you keep your alpha, or your a up front that we had there. Right, and so then if we just plug back in all of our constants, 4 pi m2 pi kt 3/2 times 3/8 root pi times. Since we're at negative 5/2, we're just gonna put the alpha 2 kt over m to the 5/2, and then just like we did before, we just went through and just started canceling everything out. You can see with the 2's, again, we're left with an extra 2 in the numerator here, but that multiplied by this 4 and the 8 will actually all cancel out. Right? And so this 3 is the only number that's going to remain. You're left with a root 5 in the denominator. I'm sorry, not a root 5. You're left with an m in the denominator. You're left with, just cancel this out. Left with a root pi down here, and it cancels out with this one here. You get k left in the numerator, t left in the numerator, and that actually cancels everything out. Now remember, this is also equal to v average squared, and so to get root mean squared, the last thing left to do is to take the square root of this. 3 kt over m equals v RMS. And when you're looking at different velocities, we know that this one is less than this one, which is less than this one on the actual graphs. And then when you actually look at these numbers, the only things that are changing is your number constant, and you have a 2. 8 over pi is about 2.5, and a 3. So that actually makes sense to be going that over to.